In this video, we're going to be talking about polynomial functions. And by definition, a polynomial function is a function of this form, which looks really confusing. It is easier than what it looks like there. What does all this mean? This a sub n minus 1, a sub n minus 2, these are just whole numbers. They're integers. They don't have to be whole numbers. They're real numbers. It could be decimals, fractions, whatever. But these x to the n's, okay, they're and x to the n minus 1, x to the n minus 2, there'd be like x to the fifth, x to the fourth, x to the third, x to the second. Now, what's so important here is your coefficients out front. Your leading coefficient here can't be 0, because if it was 0, then pretty much this term's missing. Now, you can be missing other terms, but we've discussed polynomials in the past, and that's all it is. Even though the definition here looks really confusing, we're just dealing with polynomials. Also, n must be positive integers. The n can't be fractions. We're not doing like our power functions here to where we have n to the 1/2 or 1/3 or anything like that. They're whole numbers. Also, we're not going to have any negative exponents. All these exponents are going to be positive integers. So, shape and continuity, what do these things look like when we graph them? Okay, polynomial functions are smooth curves. They have no breaks or gaps, so therefore they are continuous everywhere for all real numbers. You can plug anything into them and you're going to get a value. So there's no discontinuity. They go to infinity and they go to negative infinity. There's no breaks, there's no gaps. And that's what these polynomial functions look like. Also, they're smooth function, which means there's no kinks like an absolute value function or anything like that. They are going to be smooth curves all along the entire length of the polynomial. The degree of a polynomial function. The highest exponent n of a polynomial is called the degree. Polynomials are classified by their degrees. And here's some examples. It says on this next part, identify the degree and classify each polynomial function. So let's remind you of the different names that these polynomial functions have. On the first one, you have x to the 0 power. There's no x's, so therefore the degree here is going to be 0. And anytime you have just a number, that's called a constant polynomial, because again, it's just a constant. It's all that's there. The next degree, the highest power, is going to be 1. And this is, we remember, as y equals mx plus b. This is a linear function. Next up, your highest degree is 2. If you were to graph that, it would be a parabola. Degree of 2 is called a quadratic. Next one's highest power is a power of 3, and we're not concerned about the other terms. We're just looking for the highest power. Anytime you have a degree of 3, it's called a cubic polynomial. If the highest power is 4, it's called a quartic polynomial. And finally, if the highest power is 5, it's called a quintic polynomial. Okay, next up we're going to be talking about end behavior. And reminder, it says the power and coefficient of the leading term determines the end behavior of the function. Recall from the power functions. Okay, we want to go back and remind you on what the power functions look like. Anytime you had an even power and a positive leading coefficient, which in this case is 1, you had this basic shape. Even if it was x to the 4th, it still, as you travel to the infinities, look like this basic shape, or x to the 6th. As long as it was an even power and a positive coefficient, the end behavior was this. As we travel to the right on these even functions, your y values will always go up. As we travel to the left, your y values will also always go up. If you were to have a negative coefficient, though, it flips it down and it changes your end behavior. In this case, since they are flipped over, and again, this is not just for x squared, but negative x to the 4th, negative x to the 6th. Anytime you have that even power, as you go to the right, your y value will go down. As you go to the left, your y value will also go down. What if you have an odd power, but a positive coefficient, like a 1x to the 3rd in this case? You have this general graph. your end behavior will now be this. As you travel to the right on these graphs, your graph will always increase. As you travel to the left, your graph will always go to negative infinity. And then if you were to, again, multiply that by a negative one out front, it flips your graph over and would reverse those end behaviors. As you travel to the right, your graph would go down. And as you travel to the left, your graph would go up. So now let's apply these end behaviors to a general term, a general polynomial. Using the leading coefficient or the leading term, give the end behavior of each polynomial function. Let me remind you why you can do that. The power and the coefficient of the leading term determines the end behavior of a function. So therefore, if you want to see what is this function going to do, what's the end behavior of this function going to be, all you're concerned with is the leading term, the highest powered term. The rest of this really doesn't matter. So use that negative x to the fourth, and we know an x to the fourth is an even function. A positive even function looks like this. A negative even function, which we have here, would look like this. So as far as the end behavior goes, so my end behavior will follow the exact same pattern as this function. So therefore, on this function, as we go to the right, my y value will always go down. And as we go to the left, my y value will always go down as well. Now what I want to do, I want to take Desmos, and let's actually graph this and look and check and just show you the general shape of this and how it does follow this pattern. Okay, so on Desmos, here is that graph. And you see again, as we go to the left and right, you see it decreasing in both directions. Okay, next problem. Negative 2x to the fifth, and again, honestly, the rest of it don't matter. Negative 2x to the fifth is your leading term, the highest power, and it is a negative. Now, normally, an x to the odd power would look something like you have x to the first, which looks like this. You have x to the third, which most of the time will look something like this. X to the fifth, what you could actually do, notice what happens is each time you go up by 2 powers, a lot of times it's going to throw an extra heel in here. So an x to the fifth functions a lot of times will look something like this, but again, the end behavior is what we're worried about. That's an x to the first, x to the third, and x to the fifth. However, when you put that negative out front, it makes it go downhill. It flips it over. So it's going to look something like these. Would be a negative x to the first, a negative x to the third, and a negative x to the fifth. So the third scenario there is what we're looking at. So our end behavior is going to be this. As we travel to the right on our graph, your y value will decrease. It'll go to negative infinity. As you travel to the left on your graph, your y value will increase and it will go to positive infinity. And you can double check that with a graph. This is a simple parabola, so we already know the end behavior here. As x goes to the right, we know that my y value will increase. And as x goes to the left, we know that my y value will also increase as well because it is, increase. So because it's a parabola, and it is a positive 6x squared. X to the seventh will follow the exact same pattern. Since this is positive, will follow the exact same pattern as far as end behavior goes as x to the first. So therefore, your end behavior is going to be, as x goes to infinity, your graph will go up. And as x goes to a negative infinity, your graph will go down. But again, since it's x to the seventh, what's going to happen is there might be some heels and stuff like that in the middle of it that changes it. But again, the end behavior, the general end behavior is going to be identical. It's going to be the exact same. X to the third power will follow the exact same pattern as x to the first power. And since it is positive, you've got the same scenario. As you travel to the right on this graph, your function will go up. And as you travel to the left on your graph, your function will go down. Number 6, negative 3x to the eighth will follow, since it's an even power, will follow the exact same pattern as a parabola. However, you do have a negative out front, so it will flip it over. So your end behavior will be, as you go to the right, your graph will go down. As you go to the left, your graph will also go down. Okay, the next problem says describe both the power and the coefficient of the leading term of the polynomial given the shape. Now let me remind you again, if it's x to the first, it's going to be linear. X to the third, a lot of times we'll have one extra hill in it. X to the fifth, as you go up by 2 powers, a lot of times what it'll do is create a hill on the inside. Now this one looks a lot like this power, except for it goes in the opposite direction. So what you've got here is it's got a negative leading coefficient because it's flipped over. It goes up to the left and down to the right. So this will have a negative leading coefficient for sure. So negative leading coefficient. And also, as far as the power goes, it looks to be, since it's got not x to the first, not x to the third, but it looks like it'd probably be like an x to the fifth power. Now, we can't say that for certain. Now, I do know it's at least x to the fifth. It could be x to the seventh or x to the ninth. So if we just want to put an odd degree is for certain, but more than likely it'll be an x to the fifth there. Okay, number 8. Since you have, if you were to take out the middle part, it looks on the end like a parabola. So that's going to have to be like an even power or an even degree. Now we do know, I do want to go a step further. We do know this is not quadratic. It's not going to be x squared because an x squared would look like just a parabola, look something like that. If you've got the one extra heel in the middle, and again, this is beyond the scope. This goes a little bit further than the actual lesson. But if you've got the extra heel on the inside, most of the time, that's going to be 2 extra powers. That's probably going to be an x to the 4th power. Also, since it's not flipped over, that means that you're going to have a positive leading coefficient. Okay, next up, we're going to be talking about turning points. Turning points are the points at which a polynomial switches direction. So in this first example, notice your polynomial is going uphill and then it turns to downhill. This is a turning point. Or it's going downhill and then it switches to uphill. That's a turning point. If the turning point is higher than any nearby points, and again, all of these are a review of previous concepts. If the turning point's higher than any of the points around it, we call it a relative maximum. Now, we learned again in previous videos, if it's the highest point in your graph, we call it the absolute maximum. If the turning point is lower than any of the points around it, we call it a relative minimum, or it's the lowest point around. Maximums and minimum values are called extrema, so the extreme values. Turning points define where the function is increasing and decreasing. Notice again that your function was increasing, then it started decreasing, then it started increasing again. So using a graphing calculator to find these turning points, it says find the turning points of the function right here. Graph the function with a graphing calculator, and instead of using these steps, we're going to use Desmos and we're going to identify these turning points. Okay, so here is the function graphed on Desmos. Notice that you have this maximum point here located, this is a relative max, located at negative 447, and a relative minimum at 0.667. Now that's a rounded value, so that'd be 2/3. 0.6 repeating is what that value would be. So at negative 4 and at 2/3 is where your function turns. So what I've done is I've sketched this out on a little graph here. So my relative maximum occurred at negative 4, comma, and we can go back and check out y value 47. My relative minimum occurred at 2/3, comma, and that minimum there was negative 3.815. And you could do the negative 2/3 in decimal, or positive 2/3 in decimal too if you'd like to. So that means that it increases from negative infinity up to that maximum. Then it starts decreasing from the maximum down to the minimum, which was at 2/3. Then it starts increasing again, and it increases from 2/3 on to positive infinity.